Alrighty. So the idea here is if we're holding these blocks at rest while we're pulling on one end, these forces should be near equal to each other to balance out. So the two quantities agree numerically. I wouldn't say they agree numerically. It looks pretty, like these are pretty much the same number, but we don't have the same level of precision here. This one gives us, 3 significant figures of measurement, where this one only gives us 2. It's kind of rounding up or down here. So I'm going to say the two quantities do not specifically exactly agree numerically. The two quantities agree within experimental uncertainty, but do not exactly agree numerically. I think B's our best answer choice. Let's see the rest. The two quantities disagree by an amount that is larger than the experimental uncertainty. Not quite. And then the two quantities cannot be compared because the two force probes have different levels of precision. No, that's not true. We may think that may be the case, but here we can go ahead and say that the uncertainty is going to be about plus or minus for at least for this guy 0.1, and then the other guy is going to be plus or minus 1 Newton for the uncertainty. And we may be wondering, how did I get that uncertainty? Well, basically it's just the precision of your probe. If we notice, our first probe measures out to about 0.1 newtons, and the other guy's only going to be recording whole number newtons. Now, usually, as long as your uncertainty in one scenario is less than 10% compared to the other guy, then you're fine. That's kind of one way we can think about it. There are what we call weighted uncertainties in higher level, like experimental methods. But for now, as long as if you're comparing two sets of datas, as long as the uncertainty in one is within 10%, you're fine. This is why I keep saying good enough for government work a lot of times. Question number 5. A hockey player uses a hockey stick to hit a puck such that the stick provides an applied force on the puck. The puck travels a distance of 0.85 meters while experiencing the force from the stick. The puck leaves with a speed of 8 meters per second and travels at a constant speed in a straight line along the horizontal ice for a distance of 12 meters. The frictional force between the puck and the ice surface is negligible. How does the magnitude of the force exerted by the stick on the puck compare to the force exerted by the puck on the stick at the same time interval in which the stick is in contact with the puck? All right, let's see what we're thinking here. All righty, we have about 4 out of 6 submissions on this one. We'll go ahead and call it here. So this is what we call an action-reaction pair. The force on the stick by the puck and the force on the puck by the stick. These guys need to be equal and opposite to each other. They are what we call a third law action-reaction pair, and so this is going to be the case. Okay. So this was just kind of testing. Okay, do you know what an action-reaction pair is? And by and large, most of us were thinking that. For the two of us that maybe took a little bit of time, let me know what you were thinking, or maybe you're just still reading through them. But here we should kind of instinctively know, like, okay, if they give us a pair of objects in contact with each other, the force on one has to equal the force on the other. We just kind of like switch the words. And if those two statements still read the same, then we're fine, and they are equal. And that's the case here. Let me check the chat real quick. I was looking at the numbers, but I didn't see the answer now. But I see the answer now. Okay, all right. Yeah, so that's kind of like the gotcha here. They give us a displacement. They don't give us a force, and they give us a velocity, a final velocity after contact. So if we knew the force, actually, we could like calculate things, because we've learned that the work is the force times the displacement. And the net work will be the change in the kinetic energy in this scenario. So we could say, like 1/2 mv squared equals F times delta X, except I don't think we have a mass. And so, but we can get the acceleration. F over m is the acceleration, and that would be 1/2 v squared over delta X. which is something, but it's not really anything too useful in my opinion. So in this case, yeah, don't get, especially here, we can just stick to that principle because the numbers sometimes won't be sufficient to get us our answer. Like here, we're missing one more variable. Oops. I mean, we're going to go ahead and relaunch the poll, but thank you for sharing that. Question 6. Ooh, did I copy this one over twice? No, no, no. So this follow question now is, which of the following statements best describes the force or forces exerted on the puck after it is hit by the stick and slides on the ice? And so earlier we were told that the frictional force between the puck and the ice surface is negligible. Let's see what we're thinking. Okay, we'll go ahead and end the polling here. And so we should be seeing a scenario where there is no frictional force on the puck. Now here, B sounds really good because we should expect it not to accelerate. The problem here is the second part. There are no forces exerted on the puck at this time. The thing is, there are two forces. We have the gravitational force, which is the weight, which we calculate by N times G. And then we have the force from the floor, which we call the normal force. And these guys should be equal in magnitude. So I think D, excuse me, is our best answer. C says there's no normal force, which is true, which is not true, sorry. And then the applied force from the stick is still exerted. No, it's no longer in contact. All right, let's go ahead and look at the next one. A motorized cart and a block. So let's see. A motorized cart is attached to a string that passes over a pulley. The other end of the string is attached to a hanging block. In the figure shown above, the cart is accelerating to the right. Which of the following best represents the forces on the cart at the instant shown? So let me try to zoom out here. And all we know is the cart accelerates to the right. Oops, sorry, let me relaunch the polling. I'll call this one at 20 seconds since hopefully you've been mulling it over here for a bit. All righty. So let's see here. Because it's accelerating to the right, that tells us that the net force must be to the right. We need more force to the right than to the left. So if we look at our free body diagrams, here the force applied by the motor, or really friction, is what allows this thing to, like tug on the ground to move. And so because of that, this force to the right must be bigger than the force to the left. So that kind of leaves us with C and D. The next thing is, as far as we know, this cart is not accelerating up or down. It's not going to levitate and fly off. It's not burrowing into the table. So the normal force and the gravitational force will need to be balanced with C. So there was a little bit of variety on these answer choices. Let me know what you guys were thinking for A and D. In the meantime, we'll go ahead and move on to question 8 here. And I'll pause just in case anyone is kind of submitting their thought process there for it. So a block slides with constant velocity down a rough inclined plane that makes an angle theta with the horizontal. It experiences three forces: the gravitational, normal, and frictional forces. Which of the following gives the magnitude of the net force on the block? Let's see what we're thinking here. Oops, relaunch polling. Oh, College Board, you are interesting. I like this question. So we'll go ahead and call it here. So they want us to determine the net force or the magnitude of the net force when this bad boy moves at a constant velocity. Well, if it moves at a constant velocity, the acceleration is 0. So the net force must be 0. Let's go ahead and take a look here. If these were vectorially set up so that these were just like the normal force vectorially added with the force of friction vectorially added to the force due to gravity, then I could see this one being correct. The thing is, we would actually need to take care of the directions here for these guys. For instance, the force due to gravity actually has two components. There's Fg sine theta, which acts down the incline. And then we have Fg cosine theta, which acts perpendicular to the surface. And then so we could say this guy minus that guy is one scenario, this guy minus that guy is another scenario, but none of these give us that. So our best answer choice is 0. In case my previous statement didn't make sense, the normal force minus the component of the gravity acting into the ramp, which is cosine theta, that would be 0. And then the force of friction minus Fg sine theta, that would be equal to m times a. But more importantly, recognizing the acceleration here is 0 because it's constant velocity tells us the net force is 0. Oops. Let's go to the next one, 9. In the setup shown in the figure, 2 blocks of equal mass m are at rest but are about to slip, as shown in the free body diagram for the top block on the table. In this setup, the coefficient of static friction between the block and the table rested upon it must be see what we're thinking here. Okay, we'll go ahead and call it here. So in this scenario, we have the force due to this tension force, Ft, is going to be equal to mg. And these guys happen to have the same mass. Now they tell us that this is at rest. So if we look at this scenario, if this was perfectly frictionless, the moment that we were to let go of it, it would already be moving. And so here they tell us that they are at rest, which means that they've been sitting there for some time where the force due to gravity or friction has been keeping it from acting up. So, or from slipping. So what this tells us is that the force due to friction must equal mg. Here the tension is transmitted, or it's going to transmit the weight of the block. And so in this case, we have learned that the force of friction is mu times the normal force. And so mu here is going to be the force of friction, which we found out is mg. Let me clean that up a little bit. And then at the same time, the normal force is going to be mg. So it's going to be actually at least 1. Because we have the weight of a block pulling it this way, we need a force of friction equal to the weight of the block pulling this way. And the friction is going to be the coefficient of friction times the normal force. And the normal force is equal to the weight of this guy. So we need at least a multiplier of 1 so that this guy is a full count of the force due to gravity, because that's what's also pulling it to the right here. So that friction can create an equal and opposite force. Because if it slips, well, then it'll slip. But for now, it is at rest, keeping it from moving. And if maybe we gave it a tap, then it would start to move. Because any other scenario here, it would start accelerating. So again, let me know if there's questions in the chat. Okay, so we have 3 blocks, an applied force, tension 1, tension 2, and there's some coefficient of friction. The coefficient of friction between each of the blocks and the horizontal surface is mu. The tension in the left and right strings is T1 and T2 and T1 respectively. And the acceleration of the blocks, which, oops, I have my windows all over the place, of the blocks is A. Which of the following expressions is equal to T2? So let's see here what we're thinking. Alrighty, and we'll go ahead and end the polling here. And so if we draw a free body diagram for M3, we have T2, we have the force of friction, we have the force due to gravity, and we have the normal force. So in this case, we're trying to find T2 using Newton's second law. T2 minus the force of friction on block 3 is going to be equal to the mass of block 3 times its acceleration. And so T2 is going to become M3A plus the force of friction on that third block. Well, how do we find that force of friction? Well, that's going to be mu times the normal force. And the normal force here is going to be equal to the gravitational force of block 3. So that would be mu times M3 times G. So let's go ahead and see here which of these, say T2, is going to be M3A plus mu M3G. Sadly, if we look at this, none of these deal with block 3. So I should have probably recognized this in my answer choices and actually done the free body diagram for M2. So if we do the free body diagram for M2, we have T1, we have T2, we have the force due to friction on block 2, we have the normal force on block 2, and we have the force due to gravity on block 2, which is pretty much the same scenario. We're going to have T2 minus the force of friction on block 2 minus T1 equals M2 times A. And the force of friction here, I'm just going to rearrange this, M2 plus, sorry, M2A plus the force of friction 2 plus T1. So we're looking for M2A plus mu M2G plus T1. Which in this case looks to me like D is our best answer choice. Let me make sure I set these up correctly. Sorry, no, I fumbled here. My equation is not correct. I kind of jumped the gun here. This is minus T1, this is plus T2. Actually, we could leave it like this. And then just change this to a plus. So then this guy becomes a plus, that guy's a minus. So then when we move this over, this is a minus. Yeah, let me clean this up. This is incorrect. Let me do my equation again. Sorry about this, guys. I feel like I'm wasting y'all's time making these errors. So let's do it again. T1 minus T2 minus mu M2G equals M2A. I'm going to swap this guy over and this guy over, and we get T1 minus M2A minus mu M2G equals T2. So there we go. B is our best answer choice. Sorry about that. I was like, there's no way. Like everyone got it wrong. Like it just felt weird, and so I'm glad I checked here. Yeah. Yeah, we're gonna say this is the positive direction. Okay. Oop, let me check the chat here real quick. Why do you subtract by the force of the force of friction by T2 if they're acting in the same direction? Yeah, so sorry, Shrey. Let me know if that actually fixed it now that I rewrote my equation correctly. Why isn't it T2 plus F? Okay, all right. And then minus T1 equals M2A. Because in this case, if we look at this scenario, we can probably expect this to accelerate in this direction. So we should take this as the dominant force and this as the opposing force. So it really should be this guy minus and the force of friction also minus. We could do it the other way around as well and say T2 plus the force of friction minus T1 equals M2A. But this would have to be such that it's accelerating in the same direction as T2. So let me know there if that makes sense, Edward. So here, more than anything, I think this would probably be a minus, just because looking at this scenario, we can assume that the acceleration is in this direction to the right, while T2 is acting to the left. Okay, all right. Will I be able to use my CAS on the AP exam? Yes, you can. You can use any calculator on it. Okay. So let's see here, physics one. What would we like to do? Do we want to go from 11 to 21, or do we want to just kind of pick and choose which ones we prefer? Could you put all the equations on? Yes, you can. Yeah, you're more than welcome to do that. You could write, if I were like really into programming the TI, or really any calculator, all calculators are programmable, like scientific and up. You could program them so that like they're more functional than just text files, but you could just put them in as text files on your calculator. The thing I advise though is the time disappears very quickly. So it's good as a reference. So it's actually allowed on the whole thing. Yeah. The thing is, you don't want it's kind of like a pitfall to put all those equations in the calculator, because sometimes you'll just spend forever looking for the right one, and a lot of times the AP exam doesn't really require specific equations. It's just going to kind of require you to focus on the principles at hand or proportionalities. But yeah, you're more than welcome to. You have to go? No problem. Alrighty, have a good one. No problem. Take it easy. But for those of you guys that remain, do we want to go over like number 11? Let's see here. And they will do that to you, where you're like, for instance, if you have open book exams in college, you're more than welcome to, but a lot of the scrubs will spend forever looking for things in the book, and the people that actually know this stuff don't even need the book. Number 19, let's go ahead and jump to number 19. All right, so we have an Atwood machine here. And so we have a mass of 2m and a mass of 4m. And block A, which has a mass of 4m, is attached to a light string to block B of mass 2m. The string passes over a pulley with negligible friction and negligible mass. Yes, no rotational inertia. The block A is held a distance h above the ground. The blocks are released from rest, and block A reaches the ground 2 seconds later. The value of h is most likely. Okay, so if we look at this, because they're released from rest, the original velocity is 0. This one's combining a couple of things here from kinematics and forces. And then give me 1 second. So we're going to want to do some Newton's second law and some kinematics. And so we get delta x. Howdy, Sammy. In the meantime, I'm going to put you in the breakout room for physics 2. I'm going over a question here, some questions here for physics 1. And then I'll go and answer the free response for physics 2 on unit 1. Join the room. Sorry, let me actually leave the room. You better be working, not skipping.
Mr. Gasca, I think you're muted, sir.
Thank you. I appreciate that. Yeah, I keep forgetting that when I jump in and out of rooms, the video and sound settings kind of get changed. So in this scenario, we're going to want to do some kinematics. The displacement of that block is going to be equal to h. And all of the original velocity times time term cancels out because it starts from rest. The tricky bit is we need to know the acceleration of this. So in this case, the shortcut to these Atwood machine problems, at least these simple ones, is to ask yourself, well, what is causing this system to accelerate? And so there's going to be two forces acting on this system. There is the weight due to the 4mg block, and then there is the weight due to the 2mg block. So in this instance, we need to find out, well, what's causing it to move? Well, this guy's going to cause it to move. And this is going to oppose that motion. So we can get the net force on the system right away. The net force is going to be the difference in the weights. So it's going to be 4mg minus 2mg. And let me know if we have any questions so far. And so the difference between these two forces is what's going to cause this system to accelerate. So then when we go here, we ask ourselves, well, what is the mass that is accelerating? Well, here it's 2m and 4m that are accelerating. This is a total of 6m times a. So now we can get the acceleration. The acceleration is going to be the difference of these two, 2mg, divided by 6m. And our acceleration ends up being g over 3, which is approximately 3 meters per second squared. I wouldn't get too hung up on the 9.8 portion. And so now we can get our displacement. It is going to be 1/2 3 times 2 seconds squared. And we can put our units here. Seconds squared cancel. And, well, let me not do that because it makes it seem like the seconds or the squaring of 2 is going to cancel out. But this becomes 1/2 times 3 meters per second squared times 4 seconds squared. Now they cancel and we get 6-ish meters. And so it's most likely going to be this guy here. Let me make sure I did my math right there. 2 times 3, yeah, okay. Does that make sense? Questions about this one? And then let me check the chat real quick. I just saw that. You're muted. Yeah, whoops. Yeah, thank you for letting me know vocally. Sometimes I don't see the little thing come up for the chat. But you kind of like, especially if you have two masses hanging, you just kind of ask yourself, what's the difference in the mass? Okay, 2. Multiply that by g. Then what's the total mass? 6. So then that's going to be divided by 6. So 2g over 6 is going to be about g over 3. And so that's an acceleration of about 3 meters per second squared. All righty, what's the next one you guys would like to go over? If not, I'll just kind of choose some of these. I believe we had 16 on one of our tests modified, but all righty. In that case, I'll probably just pick up where we left off. A falling skydiver opens up his parachute. A short time later, the weight of the skydiver parachute system and the drag force exerted on them are equal in magnitude. Which of the following predicts the motion of the skydiver at that time? So the forces are balanced, but because he's been moving, he will not just be at rest. He will just maintain his velocity. So there's no acceleration, but he is moving downward, and he will be moving down with a constant speed. Next one. Which of the following figures each show vectors representing the forces exerted on an object that is initially at rest? In which case will the object remain at rest, representing an object that is initially at rest? So not this one, not this one. The forces here are not balanced. Let's see here. This guy, we can go ahead and take this amount of arrow. And then here, this guy here, this guy looks to be about twice this guy. And then let's see here, this guy. I think C is our best answer choice for this guy. If we look at D, the horizontal components of these are this guy, and then you're going to need to double that. And so I don't think D is balanced. Vertically, it balances out, but horizontally, I think we have more force acting to the right than that. Okay. A person kicks a ball into the air with a force F naught. The figure shows the position of the ball at various times. What is the net force on the ball and its acceleration at the highest point shown? So even though we kicked it, the only force acting on this bad boy is the force due to gravity. And so the force is going to be equal to mg because we are no longer in contact with it. That is no longer the case. And so the acceleration should be b equal to g. Yeah, we kicked it into the air, but our foot is not in contact while it's there. All righty, 14. Two astronauts of identical mass are connected by a taut cable of negligible mass, as shown, and are initially at rest with respect to a nearby space station. Astronaut Y pulls on the cable toward herself with considerable force. Which of the following describes the direction of the velocity of the center of mass of the two astronauts as astronaut Y pulls on the cable? So as this person pulls on the cable is going to pull them. And these forces are an action-reaction pair. So the forces cancel out and the acceleration is 0. These forces are internal to our system. So the center of mass does not move. These two will meet, especially if they have equal masses, they'll meet in the middle. Even though astronaut Y is doing the pulling, that is irrelevant. Kind of think of it this way. Let's say you're standing on skates and you happen to pull on a tree. You're going to pull yourself closer to the tree. But in this case here, the astronaut X is not a tree. They are not planted into the ground. So they're going to move towards you, but you're also going to move towards them. Kind of like, again, similar to that scenario where you're pulling yourself closer to the tree. But in this case, both of you guys move together towards the center. And because there's no external force on the system, then there's no acceleration. So the center of mass of the system does not move. Two blocks of mass 2 kilograms and 3 kilograms are connected by a light string that passes over a pulley as shown above. The pulley has negligible mass and friction. The two-block system is released from rest. Which of the following correctly describes the velocity of the two-block system center of mass? So if we look at this, we're going to have 3 kilograms moving down and 2 kilograms going up. But overall, we have more mass moving down than we do have going up. So the velocity of the center of mass is going to be directed downward. And the system is accelerating. And so there's an external force. There's a net force acting down. In this case, it would be 3 times G minus 2 times G. And so the net force here is equal to 1 kilogram times 9.8 meters per second squared. And so there's a net of force on this. And so the velocity should be increasing as we move downwards, C. Even though this guy moves faster and faster up, here this guy moves faster and faster down, and we have more mass accelerating down than we do accelerating up. And because they're moving down, or the center of mass is moving down, the center of mass velocity will be increasing. Let me just check the chat here. You have to leave? Okay, no problem. Have a good one. Take it easy. An object of mass m is dropped near the surface of the Earth such that the gravitational field provides a constant downward force on the object. Which of the following describes what happens to the center of mass of the Earth object system as the object falls downward toward the Earth? Well, just as this object moves down towards the Earth, even though it's much more massive, will feel an equal and opposite force, and it will move up. Now, because this gravitational force is internal to that system, I pull on the Earth pulls on me, those two forces are equal and opposite, and those are the only forces acting on us, assumedly. So the center of mass does not move. But because I happen to have 10 to the 24 times less mass than the Earth, And then we could say, I don't know, mass of the object is going to be maybe a kilogram, 10 kilograms or so. Maybe 1, maybe 10 kilograms, maybe 100 kilograms. But nonetheless, it's still nowhere near as massive as the Earth. And this is why the acceleration is more noticeable for the person or the object than the Earth. Alrighty, let's go ahead and look at 18. 3 blocks are sliding together to the right on a surface of negligible friction with a force of magnitude F external and is exerted to the left on the rightwardmost block as shown in the figure. The masses of the blocks are indicated in the figure and the force is exerted for a time, delta t. And the question is, what is the change in the velocity of the center of mass of the 3-block system? So in this case, we want to get the velocity, the change in velocity. So delta v over delta t is our acceleration. So we just rearrange this and we get delta v is the acceleration of the system times the change in time. Well, what's the acceleration of the system? Well, there's only one force, the external force acting on it. And then we have 6 counts of mass. So that's going to be 6m. So this delta v is going to be F external over 6 masses times delta t. And so our best answer choice appears to be A. Okay, we're in the home stretch here. For number 20, a 1 kilogram block is placed near the top of an inclined plane that is at an angle of 30 degrees with respect to the ground, as shown above. By correctly determining the effect of gravity, a student predicts that the acceleration of the block will be 5 meters per second squared. After allowing the block to slide down the inclined plane, the student finds that the acceleration is actually 4 meters per second squared. What type of force did the student most likely not account for when predicting the acceleration of the block? And what is the magnitude of that force? So we need a force that is along the inclined plane, which is going to be the force due to friction. And then the question here is, well, which of these is the magnitude for it? Okay. And then, howdy Namila, howdy Sammy. I'm actually almost done with the multiple choice. If you guys have time for the free response, we can go over it here in a bit. So we can go ahead and say, well, we know that the force acting down the incline is mg sine theta. And then we have the force of friction. And so we have mg sine theta minus the force of friction equals m times a. And we can go ahead and start substituting some things here. The mass is 1 kilogram, so that becomes 10 newtons times sine of 30. And sine of 30 happens to be a half. Then here, I'm going to move this guy over and this guy over, minus m times a equals the force of friction. Here I could have substituted in the numbers, but I felt it might confuse some people. So this becomes 5 newtons minus the mass, which is 1 kilogram, times an acceleration of 4 meters per second squared, equals the force of friction. Sorry, let me clean that up. Looking at this, hopefully we see here that that's 5 newtons minus 4 newtons is the force of friction. And so B is our best answer choice. Okay. And again, let me know if you guys have questions. And then lastly, question number 21, they tell us a 3 kilogram object experiences a rightward acceleration of 6 meters per second squared as it slides to the right across a rough horizontal surface. The table above contains the label and the magnitude of 4 forces exerted to the right or the left of the object that represent measurements from an experiment as the object accelerates. Which pair of opposing forces in which directions could be responsible for the acceleration of the object? So the net force here is going to be equal to m times a, which tells us that this is 3 kilograms times 6 meters per second squared. And so this should be about a net force of 18 newtons. Okay, so let's see here. So we need to find a situation where the net force is 18 newtons. And any one of these, it looks like F2 and F3. If I have, and it's accelerating to the right. So we need F3 equal to 24 newtons to the right. And then if we subtract that from F2, which would be 6 newtons to the left, that gives us 18 newtons. So wham, bam. F3 to the right and F2 to the left. And so hopefully that takes care of the multiple choice B.